Good morning, my dear students. Now, this is the lecture number 7 in our communication or introduction to communication model. One lecture far from the course termination. In the previous lecture, or actually 2 lectures ago, we have studied what's called that signal digitalization. How to transfer our analog message into a digital message. Then, in the previous lecture, lecture number 6, we introduced the concept of digital modulation through what's called the shift keying techniques. And then we introduced also what's called the pulse modulation techniques, including the pulse amplitude modulation, the pulse position modulation, and the pulse width modulation. And in the last phase in the previous lecture, we introduced also what's called the multiplexing techniques. Now, in this lecture, lecture number 7, we will upgrade our knowledge about the modulation, or I mean digital modulation techniques, through upgrading the shift keying techniques from the amplitude shift keying, the phase shift keying, and the frequency shift keying to what's called the quadrature amplitude modulation. So please accept my invitation to share my presentation slides and start lecture number 7. Okay, perfect. I believe now you can see my presentation slides, and let me also open my laser pointer in order to start this lecture under the title Quadrature Amplitude Modulation. Okay, perfect. So I think now the laser pointer is working and we can now start our lecture number 7. Okay, perfect. So as I just mentioned, in the previous lecture, we deal with what's called the pulse amplitude modulation, the pulse position modulation, the pulse code modulation, the pulse width modulation, and all these stuff. Also, we introduced the concept of what's called the Constellation diagram, if you remember this Constellation diagram. This diagram representing the phase and the amplitude of the bit. So, for example, when we deal with the binary phase shift keying, if you remember, we say that we have 2 states, what's called the 0 state and what's called the 1 state. And we represent the 0 with a carrier with a certain amplitude, constant amplitude, and a phase 180. That's why in the Constellation diagram, we introduce this point here, because this vector, or the direction of an x-axis, represents the 0 angle, or what sometimes we call it I, or the in phase. This represents the 90-degree angle, or what we call it Q, or the quadrature. And then this is 180 and this is 270. So whenever you are going to represent an amplitude, the amplitude is represented as the distance between the origin and the point. So this is the amplitude. And the phase is here. This is located on the negative axis, negative x-axis, I mean. So this is simply represent the 180 degrees. Similarly, the 1 state can be represented in this manner. So now it's a 0 phase with the same amplitude. This is what we call the binary phase shift keying, or the ppsk. This was one of our previous lecture slides. So whenever you are going to implement this is on a stream of bits, so this is a 110101. So the ones are represented with, as you can see here, this is the output. So this is the ones are represented with a 0 phase. However, whenever you have a 0, this 0 is represented with a negative 180 or a 180 phase, as you can see here. So by detecting the phase of the signal at the starting of the bit, you can demodulate the output stream of bit, either it's a 0 or it's 1. This is what we call the binary shift key. Okay, now we are going to upgrade this technique. What I mean here by upgrading is transmitting more data in the same time duration. Again, transmitting more data in the same time duration. So in order to explore this idea in more details, let's examine it. So let's say that this duration what we call the TP, or the duration for one bit, is, for example, 1 second. So in this ppsk model, you are transmitting 1 bit per second, because in this duration, which is the TP, you are transmitting only a bit. Or another word, you can say that your symbol is 1 bit. So you are transmitting 1 symbol per second, and your symbol includes only 1 bit, so it's obviously 1 bit per second. Is it possible to transmit more bits in second, in the same time duration, which is in our example 1 second? Is it possible to transmit more bits? Yes, this is possible by using another modulation technique. One of these modulation techniques, my dear students, is what's called the quadrature phase shift keying, or the QPSK. In the QPSK, instead of having, I'm sorry, I went to the wrong direction. So in the PPSK, we have 2 simples. So we have 2 states. That's why we have 1 bit. Because you can easily understand. Let me go now to my whiteboard. Okay, no, this is my whiteboard, I think. That's perfect. I believe it's somehow adjusted. So we can stop sharing for a while, and we can go to using this. Okay, so for the constellation diagram, whenever you have I'm sorry, I'm just trying to search for another color. Okay, whenever we have 2 states, then you can represent only 1 bit, because simply 2 power n is equals to L. L is the number of states and n is the number of bits. So whenever we have 2 states, then you can represent only 1 bit. This is very logical. What if I have a constellation diagrams looks like this? So this upper one represents the binary phase shift key. What if I have another constellation diagram with this? So I have 4 bits. Still I have 4 states. Still the 4 states are with the same amplitude. So again, the amplitude is represented at the distance between the origin and the point, this radial distance. So as far as these 4 points are located on the surface of the same circle, so they are, all of them have the same amplitude, which is, for example, AC is amplitude of a carrier. Now you have L equal 4. You have 4 states. Then you can represent 2 bits, not only 1 bit. You can now represent 2 bits. So, for example, I would say this representing on 1 1, and this representing a 0 1, and this representing 0 0, and this representing 1 0. So these are the 4 bits representation. Now you have 4 different versions of the carrier. This simple represent a carrier with a phase shift 45 degrees. This represents the one state. This one represents a carrier with 135 degree shift. And again, this is with okay, so this is 135. So this will be 180 plus 45, which will be 225 degrees, and then this will be 360 minus 45, which is 315 degrees. So you have 4 different phases. Each phase will represent 2 bits, or a symbol of 2 bits. So let's now turn again to my PowerPoint slides. I'm just trying to operate my pointer. Okay, I believe there's somehow a problem. Let me, I make a wrong share, so let me make it right. Okay, I think this is now a full screen presentation. So let me hear. Yeah, so this is the four states. These four states located on the same outer circumference of a circle. I mean the distance between the origin and the points on the 4 points are identically. So they have all of them have the same amplitude, but they have a different phases. This is can be represented here. So for example, in the 1-1 case, this is a 45-degree shift. For the 0-1 case, you have a 135-degree and so on. So you have four versions of the carriers. Each one represents a state, and each state represents 2 bits. So simply, whenever you transmit this signal, which is a sinusoidal signal with a 45-degree shift, that means that this represents a state of 1-1. Yeah, I think now you can capture the difference between the QPSK and the ppsk. In the ppsk, let me return 2 states. Yeah, in the ppsk, in the one duration, in the one sample duration. So now it's better to call it TS, actually, not TB. TS, I mean the duration for one sample, or for one symbol, actually, not sample, the duration for one sample. So here, the duration for one sample includes 1 bit. However, using the same duration of one sample, you are now sending a symbol of, or for one sample, sorry, not sample, you are now sending a symbol of 2 bits. That's obviously mean that you double your data rate. Here, in the TS, which is, for example, 1 second, you are transmitting 1 bit. So your data rate is 1 bit per second. However, here, you are transmitting 2 bits in seconds. So you have a double data rate with respect to the ppsk. So this is the main advantage of the quadrature phase shift keying over the binary phase shift keying. You can extend the theory to include, let me go here. Yeah, for example, this, no, I'm sorry. Okay, so this is an example. I return back to the slide. So this is another example. Now we have 8 PSK. So what I mean by 8 PSK, my dear student, is I have 8 samples. So whenever you have an 8 states, then this can represent 3 bits. As you can see now, the difference between each symbol and the next one, or each state and the next one, is 45 degrees. While in this case, yes, the difference between each one and the neighbors is 90 degrees, while here the difference is 180 degrees. So you can reduce the distance, or the angle between each 2 successive states in order to increase the number of transmitted bits. Here, in the binary phase shift keying, you have 1 bit per duration. However, here you have 2 bits per sample, or per duration. And finally, here, I'm sorry, yeah, here you have 3 bits per duration. So you are increasing the data rate. Again, our fixed code everywhere. No free lunch. You gain something, which is that you increase the data rate of your system. However, you lose something, which is your noise immunity. What I mean by noise immunity? Okay, so let's explore it in detail. Okay. Let's stop sharing for a while. Let's now use a new paper to explore. Let me make a comparison between the binary phase shift keying, the quadrature phase shift keying, and the 8 PSK. Okay. Here we have 3 constellation diagrams. In the binary phase shift keying, you have only 2 states. This is the 0 and this is the 1. Herein, you have 4 states. So you have 1, 1, 0, 1, 0, 0, 1, 0. And here you have 8 states. Again, don't forget that all these states are on the same, or are on the outer circumference of a circle. So all of these states are with the same amplitude. That's why we still call it PSK. As you can see, this is the ppsk, and this is the QPSK, and this is the APSK. All of them are an extended version of the PSK. Why we call the PSK or the phase shift key? Because simply you are only changing the phase, no change in the amplitude and no change in the frequency. You are only changing the phase of the carrier. That's why we call it the PSK. Okay, so we have these 3 versions. As you can see, for example, this is 111, 110, 100. So this is 000, and so on, blah, blah, blah. Okay, so in order to make a comparison between these 3 types or these 3 versions of a modulation techniques, you can easily say that here's a symbol includes 1 bit. And here is a symbol includes 2 bits, and here's a symbol includes 3 bits. The symbol is each state of time. Okay, but here the angle between each successive, okay, so let me use a third color here. The angle between each successive symbols or states is around 180 degrees. While here the angle is 90 degrees. While here the angle is a 45 degrees. Okay, so where's the problem to have a narrower angle? Simply, it's a noise immunity problem. Why? Now, for example, if I'm using a ppsk, okay, and then I'm transmitting a1 is represented by a signal like that, a sinusoidal signal with 0 phase, very basic. During the channel, due to some reason or another, this signal has been affected by a 25-degree shift. Then what will happen? What will happen is that this signal will looks like that. You will have another sinusoidal signal with 25-degree shift.